Hello students, in this video I am going to talk about the sequential circuits. The first sequential circuit which I am going to discuss now is latches. I will be discussing the building of latch with the help of NAND gate as well as NOR gate both. So let us start. First is, what do you understand by sequential circuit? So a sequential circuit refers to a special type of circuit. In sequential circuits, the outputs depends upon the combination of both present input as well as past output. That is the definition of a sequential circuit. So what is the difference between a sequential circuit and combinational circuit is that in combinational circuit, output just depends upon the present input. As you can change the input, the output keeps on changing. Whereas in sequential circuit, output not only depends upon the present input, but it also depends upon the past output. So that is the difference between sequential and combinational circuit. Now, what is a latch? A latch is a temporary storage device that has two stable states. That is why it is also known as bistable. And now, what are those two stable states? One is known as reset. Reset means 0, and the other is known as set. Set means 1. So it is a basic form of memory. Memory means to store the data. Next is SR latch. S stands for set. Set means 1. R stands for reset. Reset means 0. So SR latch stands for set reset latch. The set reset latch is the most basic type of latch that we have. It can be constructed from NOR gate or NAND gate, and it has already been discussed with you that I will be discussing both the types in this presentation. So here comes the block diagram of SR latch. So we have S input, we have R output, and we are going to have two output signals over here. One is known as Q and the other is known as Q bar. So make sure students that Q and Q bar both are going to be opposite to each other. That is why I have written Q and Q bar, not any other variable. So if Q is 0, Q bar must be 1, and if Q is 1, Q bar must be 0. And this bubble is representing the NOT operation, the NOT output. So this is the block diagram of SR latch. So now, before starting the discussion on the topic of SR latch using NAND gate, let us try to discuss the basic operation of a NAND gate. What is a NAND gate? First of all, this is the symbol. I have taken two inputs in the NAND gate AB. This is a symbolic representation of NAND gate, AND gate with a bubble, and Y is the output. So here I have taken A and B as the input signals, and I have written all the four possible outcomes that we can have. 0, 0, 0, 1, 1, 0, 1, 1. So what is the NAND gate output? Reverse of AND gate. So what is AND gate? AND gate says that when all the inputs are high, output is high. In rest of the cases, output is low. So in NAND gate, the reverse is going to be true. That is, when all the inputs are high, that is 1. Output is 0. And in rest of the cases, output is 1. This is the truth table of NAND gate. Also students, you can refer my previous uploaded videos based on the logic gates, and where I have actually explained all the basic logic gates, universal gates, etc. So you can refer over there as well to understand all these concepts again. But this is the NAND gate truth table. Now let us try to find out some conclusion out of this NAND gate truth table. So my conclusion is that if minimum one input is 0, I repeat, minimum one input is 0, output must be 1. So this is the conclusion with the help of NAND gate we have taken, which will help us to understand the working of latches and flip-flops properly. So once again, the conclusion says that minimum one input is 0, output must be equal to 1. So we need not to check the second input signal if minimum one input is equal to 0. So now here comes the SR latch using the NAND gate. In latches, we will be using two gates, So here I have used two NAND gates, gate number 1 and gate number 2. This is input S, gate number 2. This is input R, gate number 1. So what do you understand by sequential circuit? Where the outputs are Q and Q bar, where the outputs depends upon the present input, that is S and R, also depends upon the past output. For the past output, the feedback arrangement has been connected over here. So what is the feedback arrangement? You can see Q has been given as input to gate number 2, whereas Q bar has been given as the input to gate number 1. So this is known as sequential circuit, where output not only depends upon the present input but on the past output as well. Let us start the discussion on the truth table, that what is going to be the output of this SR latch using NAND gate. So here I have written a blank truth table over here, where S and R are the input signals and Q and Q bar are the output signals. Make sure, students, that this below signal is S and the above signal is R. S means set and R means reset. Now I am going to discuss case number 1. Case number 1 says when S is equal to 0 and R is equal to 0. So that is S is equal to 0 as well as R is equal to 0. So I have written both the signals to be equal to 0, case number 1. As already discussed, students, that when minimum one input is 0, in the case of NAND gate, output must be equal to 1. So for gate number 1, minimum one input 0, true, the output is going to be 1. Similarly, gate number 2, minimum one input 0, output is going to be 1, as per the previous discussion. Now the conclusion says that Q is equal to 1 and Q bar is also equal to 1. But I have already informed you that Q and Q bar must be opposite to each other. We cannot have Q and Q bar to be equal to each other. Hence, this condition is known as invalid condition. Invalid means it is not practically possible to have Q and Q bar to be equal to each other. Hence, this is known as invalid condition. Case number 1, when S is 0 and R is 0. Next case, case number 2. Now case number 2 says when S is equal to 0, let me mention it over here, S is equal to 0 and R is equal to 1. So now this is our case when S is equal to 0 and R is equal to 1. Now let us again try to simplify this case number 2 on SR latch using NAND gate. So in gate number 1, R is equal to 1. So we are unable to satisfy the conclusion from the NAND gate truth table, where I have discussed minimum one input is equal to 0, output is 1. So we are unable to simplify gate number 1. Let us talk about gate number 2. Gate number 2 says that minimum one input is 0 condition is true because S is equal to 0. Hence, minimum one input is 0, output is going to be equal to 1. So we are able to simplify gate number 2. So Q bar comes out to be equal to 1. So now students, you can see that Q bar is actually being connected as the input to gate number 1. So this signal 1 will be transferred over here. So 1 1, the output of NAND gate. Once again, 1 1, the output of NAND gate is 0. So this is known as our 0 1 condition, output is 0 1, and this is known as reset condition. Why reset condition? As you can see, your reset is high, so the output is reset. Reset means 0, and Q is our main output signal. Hence, this is known as reset condition. Case number 2. So this is our case number 3. So the case number 3 is S is equal to 1 and R is equal to 0. So I have mentioned both the signals over here on this SR latch input signals. So let us discuss the same case once again. Minimum one input 0, condition is true, output is 1. Minimum one input is 0, which is not true. So we are unable to simplify gate number 2. So let us drag the signal Q as the input to gate number 2. So this is 1. So 1 1, the output of NAND gate is 0. So that means when S is equal to 1, R is equal to 0, output Q is 1 and Q bar is 0. So students, this condition is known as set condition. So what is set condition? When set is 1, S stands for set. Set is 1, the output becomes equal to set. Set means 1. So this is the 3 conditions for SR latch using NAND gate. Now here comes the last condition. The condition is when S is equal to 1 and R is equal to 1. And this condition is little bit tricky to understand. S is equal to 1 and R is equal to 1. So as per the conclusion which I have just discussed with you students, that when minimum one input is 0, then only output is equal to 1. And we are unable to get the same condition in both the gates. S is 1, R is also 1. So we are unable to simplify gate number 1 as well as gate number 2. So in such conditions where we are unable to simplify any of the gate, the solution is assumption. This is known as assumption because we are unable to start the simplification for both the gates. So we are going to talk about the assumptions now. So what assumption we can take? Obviously we can assume that what was my previous output, and I can only assume 2 cases. The first case I can assume is Q is equal to 0 and Q bar is equal to 1. The second case I can assume is Q is equal to 1 and Q bar is equal to 0, which I will be discussing later on. And we can only assume 2 cases, either 0 1 or 1 0, because Q and Q bar must be opposite to each other, either 0 1 or 1 0, and they cannot have the same value. Hence we cannot assume 0 0 and 1 1. So let us start with the first assumption. Let us assume the previous condition, Q 0. So 0 will be taken and will be given as the input to gate number 2, and Q bar 1. So 1 will be given over here. So what is the output of NAND gate when both the inputs are 1 1? So 1 1, output is 0. 0 1, minimum 1 input 0, output is 1. So students, this says that if my previous output was 0 1, the next output will also become equal to 0 1. Now let us discuss the second assumption. The second assumption is 1 0. Again, S is equal to 1 and R is equal to 1. So let me discuss the second assumption. The second assumption is 1 0. So here I have taken 1 and Q bar is 0. So Q bar will be given over here. So for 1 0, minimum one input is 0, true condition, output is 1. 1 1, output for the NAND gate is 0. So now here comes my second assumption. I have taken the second assumption as 1 0 and again I am getting 1 0. So now just try to understand the conclusion. The conclusion says that if my previous output was 0 1, the next output will also become 0 1. If my previous output was 1 0, my next output will also become 1 0. So that means my next output is just following my previous output. So such conditions are known as no change condition. No change means my output is not at all changing. It is just following its previous output. So the previous output was 0 1, it will remain 0 1. If my previous output was 1 0, my next output will remain 1 0. The next second type of latch which I am going to discuss is with the help of NOR gate. But before starting that, let us discuss a NOR gate truth table. So this is your NOR gate. NOR gate is a combination of OR gate with NOT gate, as you can see a bubble over here in front of an OR gate. So I have taken again 2 inputs A, B, and I have written all the 4 possible combinations that we can have: 0 0, 0 1, 1 0 and 1 1. So what is NOR gate? NOR gate is the opposite of OR gate. So in OR gate, when all the inputs are low, that is 0, then output is 0. In rest all the cases, output is 1. So the reverse is going to be true in the case of NOR gate. That is, when all the inputs are low, then output is 1. and in all the remaining cases output is 0. Now again, let us try to conclude some conclusion which will help us to discuss the working of SR latch using NOR gate. So the conclusion says that if we have minimum one input to be equal to 1, I repeat, the conclusion says that when we have minimum one input to be equal to 1, then output is 0. So we need not to bother about the second input if one input is equal to 1. So the output must be equal to 0. So let us start. So this is the SR latch using NOR gate. The whole structure is exactly same. So the signal is S, this above signal is R. The feedbacks has been connected, but the only difference is I have replaced my NAND gate with NOR gate, and then we will try to understand that what is the difference between SR latch using NAND gate and NOR gate. So let us discuss the first case. The first case is when S is equal to 0 and R is equal to 0. Now as per the discussion which I have just done, the conclusion for NOR gate, it says that when minimum one input is equal to 1, then only we can simplify the gate. As you can see, I have just discussed when minimum one input is 1, then only we can simplify the gate. The output is equal to 0. But unfortunately, we are not having any input to be equal to 1. So 0, here as well 0. And as you know that if we are unable to simplify any gate, the result, the conclusion for that is assumption. So the first case I am going to start with the assumption. Let us take the first assumption. The first assumption I have taken 0, 1. As you know, we can only take two assumptions, either 0, 1 or 1, 0. Here comes our first assumption 0, 1. So 0 will be given over here and 1 will be given over here. 0 dot 1, just see the truth table, 0 and 1, the output is 0. On the other hand, 0, 0, when both the inputs are 0, 0, output is 1. So that is when I have assumed 0, 1, I am getting 0, 1. Let us discuss the second assumption. The second assumption I have taken 1, 0 and the inputs are 0, 0. So Q is 1, so Q will be given over here. Q bar is 0, so will be given over here. So 0, 0. Again, I am repeating this. I am discussing the truth table of NOR gate, which is reverse of OR gate. So for 0, 0, output is 1, and for 0, 1, minimum one input is 1, output is 0. Now students, just try to understand the conclusion. The conclusion is, if my previous output was 0, 1, next output will remain 0, 1. If my previous output was 1, 0, then also my next output will remain 1, 0. And such cases are known as no change condition. No change means my next output is just following my previous output. The second case, case number 2, when S is equal to 0 and R is equal to 1. So can we simplify gate number 1? Yes, definitely we can simplify gate number 1, because as per the conclusion for the NOR gate, if minimum one input is equal to 1, output will be equal to 0. Although we cannot simplify gate number 2 because we are not having minimum one input to be equal to 1. But yes, we can drag this Q signal from the output till here, which is equal to 0. So 0, 0, the truth table of NOR gate, 0, 0, output is 1. So when S is equal to 0, R is equal to 1, output is 0, 1. So that is known as reset condition. What is reset? When reset is high, output will become reset. Reset means 0. The third case is S is equal to 1 and R is equal to 0. Now students, we are unable to simplify gate number 1 because the condition says minimum one input is equal to 1 is required. Although we can simplify gate number 2 for sure, because minimum one input is equal to 1. This condition is true. So the output will be equal to 0. Now let us connect this Q bar with the input to gate number 1. So I have written 0 over here as well, taken from here. So 0, 0, output is 1. So this is set condition. For S is equal to 1, R is equal to 0, output is 1, 0. 1, 0 means when set is high, the output Q becomes set. And the last condition is 1, 1. So S is equal to 1, R is equal to 1. We can definitely simplify gate number 1 because minimum one input is equal to 1, output will be equal to 0. Also, we can simplify gate number 2 as well because it is also satisfying the condition minimum one input is equal to 1. So output will become equal to 0. Now what we are getting? We are getting Q and Q bar both equal to each other, which is equal to 0, which is practically not possible because Q and Q bar must be opposite to each other. Hence, this condition is known as invalid condition. So in the next coming video, I will be discussing the working of flip-flops as well as their conversions. Thank you so much.